Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for students who are going through differential equations and they've just begun. They're just learning about separation of variables and separable equations. And here we are within that information or that section. And this problem is usually left, in fact, for my students as an out of class lecture or something like that. It's more of just a review of integration techniques. So let's go ahead and use our old school integration techniques combined with our new skills of using separation of variables to solve differential equations. So find an explicit solution to the IVP, the initial value problem listed below right here. Now, hopefully at this point, you were able to recognize that you can separate variables here. I'll multiply both sides by y, and then I'll use the differential to go ahead and write dx to the other side. Now, you should remember that really it is not the case that you're multiplying both sides by dx here. That is actually not true. You cannot multiply both sides of this by dx to break apart dy dx, because the fact is, as your instructor probably should have told you, ddx is an operator. It does not unstick. You cannot pull that apart. Just like plus is an operator, you cannot break that apart into a minus in a vertical line. It just doesn't work like that. However, way back in differential calculus, you learned a beautiful fact that dy, the differential of y, is equal to the derivative of your function, where the function's actually equal to y, times dx. That is the differential notation. Now, in our case, our function is called y, so we could technically rewrite this as dy is equal to dy dx, which is the derivative of y with respect to x, times dx. And that's actually what we're doing over here. I happen to know that dy dx is just this picture right here. And so I could technically rewrite that whole entire equation as follows. dy, the differential of y, is equal to something times dx. That something is actually dy dx. And from here, you just multiply both sides by y. So note in that process from step 1 to step 2, I did not actually multiply both sides by dx, even though visually it kind of looks like I did. And that's where most instructors kind of give up talking to students about it, and they just say, fine, you can visualize that I multiplied both sides by dx, but I actually didn't. So that's important for me to reiterate here. I'm not actually multiplying both sides by dx, I'm just using the definition of the differential that you see off to your right-hand side. That all being said though, not that big of a deal. Now it's our turn to go ahead and integrate both sides of this equation. Now obviously the left-hand side is pretty easy to do. We're experts at this point. However, if you're not in my class, your instructor might or might not have gone over the following. Every time you evaluate an indefinite integral, you get a constant of integration. When we finish integrating that right-hand side, we'll get yet another constant of integration, and constants of integration can be added together to become new constants. We'll talk about that more in a moment. But now let's focus in on integrating this bad boy right here. And again, like I said, the whole purpose of this video is to make sure that you remember how to integrate, in this case, by parts, because this is a product of two functions, and you happen to know the derivative actually of both of these functions, the derivative of x, and you happen to know the derivative of tangent inverse. And what I like to tell my Calc 2 students is that when you're using integration by parts, you generally would like to pick dv to be the largest factor that you can actually integrate, or the most complex looking factor that you can actually integrate. In this case, if you look at those two functional factors, if you will, you technically don't know how to integrate the tangent inverse offhand. I mean, you might, but generally speaking, most people don't. On the other hand, you do know how to integrate x. So in my opinion, I would let x be what you integrate. In other words, we'll let x equal dv here, and we'll let the tangent inverse of x be the function we differentiate. Let's go ahead and do that work off to the side. Now, I may be a classic instructor in that I require my students to remember quite a bit. It is important that you know how to differentiate all different styles of functions. In fact, at this point, if you're watching a video on differential equations, you should definitely know how to differentiate pretty much anything you're handed. Integration, on the other hand, is just a whole different ball of wax. Now, we all agreed dv, what we're going to integrate, is going to be played by x, but don't forget the little dx there, because whatever you integrate has to involve a differential. So let's go ahead and integrate that dv. It'll lead us to v is equal to x squared over 2. In these cases, you don't have to worry about the constant of integration. You should have learned that in your Calc 2 course. So at this point, we can just go ahead and use integration by parts. Remember, integration by parts leads us to this formula right here, uv minus the integral of v du. We get down to this guy right here. That's actually not too terrible looking, and you should know there are quite a few little tricks to integrating something like that. One, probably most people are going to do, is just do long division, and that would make that a much easier fraction to deal with. Another little trick you could totally do here, and I kind of dig this trick, so if you are okay with the long division idea when your numerator of your integrand, well, let's back up and just say, if you have a rational function as your integrand and the numerator and denominator have the same degree, it's often told to you, yeah, do long division, and then it would simplify out. However, there's a cool little trick you can do. Note that the denominator is 1 plus x squared, so I'd like the numerator to be that as well, just so it would cancel. So I'm going to go ahead and add and subtract 1 to the numerator. In other words, I'll have x squared plus 1 and then minus 1 in that numerator. And that's a really cool little trick, because then you can break up that fractional integrand into that business right there. And now it's pretty easy to find the antiderivative of that. Now remember, we also have another constant of integration. So there's a chain of equalities here. And let's go ahead and actually just make them look really nice, put them next to each other. And at this point, you can see I have a lot of fractions. What I'm going to go ahead and do is multiply both sides by 2. Now, here's the cool thing about this move is that when you multiply everything by 2, obviously the 1/2, all the denominators, in those fractions disappear, but also twice a constant is just going to be yet another constant. You can call that c sub 3 if you want to. Likewise, I'm going to call this one on the back end c sub 4 because it's actually twice c sub 2. The other thing I want to do is maybe just go ahead and move this c sub 3 over to the right hand side. And when you take a constant and subtract it from another arbitrary constant, it just becomes, well, another arbitrary constant. Notice at this point, I stopped with the subscript notation on the arbitrary constant because, well, I kind of know I'm not going to go any further with the constants there. Now you may think, I'm done. And that is kind of true if I was solving the differential equation. So if I had a differential equation initially, so let's just pretend it was just this, then I would technically be done. I'd have a single parameter family of solutions to this differential equation right here. And that single family parameter of solutions would be this mess right here. That's an implicitly defined solution to our initial differential equation. In fact, a single parameter family of solutions that in implicit form. However, because they gave us an initial value problem, let me go ahead and zoom in here, they told us that when x is 0, y is 3. So I'm going to go down here and I'm going to go ahead and let x equal 0 and y equal 3. And it cleans up very quickly. C is equal to 9. Now, some people will tell you to solve for y before you do that. It's totally fine if you do that. That's absolutely okay with me. However, I'm not going to. I'm going to just get to this point right here and then resubstitute that back into our implicit solution and then talk to you a little bit more about how we can rewrite that. All right, we get down to this. Now, if they told us, and I don't know if they did. Oh, they did. If they told us to find an explicit solution to our IVP, that means we don't want that implicit form of y squared equals. we want y equals. So this is going to involve a little bit of thought process, not much, but just a teeny little bit. You may look at this and say, well, of course, I know what's going to happen. You're going to take the square root of both sides. But the problem is, when you take the square root of both sides, it's not a function, right? You get a plus or minus square root. And you stare at that and you think, well, unfortunately, that's not an explicit solution because it gives me two options. Explicit solutions should only give you a single option. Now, if the video jumped a little bit there, it's because I was going to go a certain direction with this, but I decided, you know what, I like where I'm at here, so I will continue with my conversation where I left off, which is, let's go ahead and figure out which of those plus or minus signs it is. Is it the plus sign or the minus sign? And that all hinges on the initial condition. The initial condition that was handed to us was x equals 0, y equals 3. Well, I gotta be honest with you. The only way to get an output of a positive 3 is if we throw out the negative version of that solution. So our full explicit solution for that given initial condition is y equals the positive square root of x squared tangent inverse of x minus x plus the tangent inverse of x plus 9. Let's see if they had us do anything else here. I don't think I did have us do anything else here, but just triple checking by zooming out. Enough? Nope. Just find the explicit solution. And that's it. All right, everybody. I hope you have a good day. Be good human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.